What is the feedback? So feedback pattern, like the author, right, in his book, Razavi just give an example. We know very well, like a teenager who drive a car, and then first time very excited, and then you drive very fast and faster, more excited, right? And eventually what happened? We think in the good way. We think in the good way. The best way we can think of is they got a ticket, right? And then the ticket will go to his or her parents. And then what happened to their parents? Of course, to give him or her a feedback, right? And we expect there must be a negative feedback. It's not going to say, oh, cool, I eventually got a ticket for our family. No, right? There's a positive feedback. Then they're going to take away his or her allowance or whatever, no driving for 5 days a week or whatever, right? And then he will slow down. So that is a feedback system. So what we're studying is a negative feedback, right? So just like here, what you're saying that is the teenager so excited, keep pushing the pedal, and then you have this amplifier, keep going faster and faster. And then someone need to sense it. Unfortunately, it's the radar from the police. And then they are going to give some feedback. How do they give feedback? Well, only 1 mile, exceeding 1 mile, maybe just stop him and just say something. 10 miles, maybe $200. 20 miles, 500, right? 30 miles, maybe just take away the license. I don't know, right? And this figure is going to come back. It's negative to subtract the original intention of the teenager so that it won't put so much force on the pedal in the future. Then eventually you have a stable system, right? Everyone don't drive fast is because of ticket, not because we think about safety. And the freeway is so safe now. So in this system, we have 4 parts. One is the feed-forward system. This is what we have spent almost 90%, 99% in the last 4 years in this degree for feed-forward. We keep making something better, faster, more efficient, right? Of course, you have took some control class that is different. And then sensing, and then feedback. Sensing is you need to think of a way to measure it, and then feedback. Now, remember, this is a circuit. You cannot say, let me buy an Android and then have to hook up the wire to there, and then, of course, I can sense it. But no, this is a circuit, a tiny circuit in your chip. You cannot do that. You need to have some innovative skill, innovative way, rely on physics to help you to sense it, right? And then provide a feedback. You, again, cannot have a MCU, the multi-processing unit, and then do the calculation and then do the feedback. Again, you want to rely on some physical mechanism. And then do a comparison. Again, you cannot do subtraction because it's not doing digital signal processing. You can do subtraction, right? So this part will be an analog circuit, usually. And very tiny. You don't want it to overwhelm the feed-forward system, right? Because it's going to take a lot of energy and area. So we have 4 parts: feed-forward, sensing, feedback, and comparison. So there's one quantity called feedback factor. It's called K. It's divided by XF divided by Y. Okay? Well, whatever you have, I multiply by K, then I give it back the feedback factor. Is this okay? Just a definition. And it's a very normal definition, reasonable definition. And this is a negative feedback because whatever going to put into the feed-forward system is not my original effort. It is Z, which is equals to X minus XF. My effort minus the feedback. Okay, and of course, XF is Y times K. Okay. And then here we have the so-called open loop gain, means you don't form the loop, you stop it. And then the gain, of course, is equal to A1. Again, this is the amplifier you always try to improve in the past, right? But our purpose is that maybe I can say that this is equal to Y divided by Z, right? Whatever come here, multiplied by A1 will be Y. Is this okay? But now we care about the overall feedback system, right? Because for us is that I want to use this circuit for some purpose. What is the gain? We call it the closed loop gain. And this is defined as ACL equals to Y divided by X. Because my true input is X, my true output is Y. It's okay? So what is this? So let's just try to derive it. Okay, I know Y equals to A1 times Z, right? Just go for the root. Is it make sense? How about what is Z? How do you find Z? X minus XF, right? Just step by step. But I still don't know what is XF, right? So what is XF? Y times K, right? Okay. And then stop here. Don't keep going. Right? It will take you many years still have not finished. So now we have an equation Y equal this one. I have X and Y there already, right? Y equals to A1 times X minus YK. So because of this, I'm going to rearrange it. Y plus A1KY equals to A1X. A1X and then A1KY, I move to the left. Then it becomes Y plus A1KY. So Y equals to A1 divided by 1 plus KA1 times X. Okay? So the gain equals to A1 divided by 1 plus KA1. Is this okay? The gain still related to the original gain, A1, but it's reduced by 1 plus KA1. This is another equation I want you to memorize. It's just that you did not learn anything if you cannot memorize this one for feedback. 1 plus KA1. And it's not difficult. You only have A1 and K in this circuit. What else can you get? Right? And don't tell me you memorize as KA1 squared if you cannot memorize KA1, right? 1 plus KA1. You will see that's going to be very useful later. Okay. Let's take a look at an example. What type of amplifier is this? Many of you were able to tell me in the first class. This is just op-amp. I'm asking the long, okay, don't think about feedback. Long inverting amplifier, right? That's what we studied earlier. And we use the KCL, KVL, and the op-amp property to derive this equation with when A0 is not infinity, finite gain. Now I can treat this as a feedback, and that will be very fast. This is the input. The input is going to subtract this one and fit to A1 to get a Y. And then there's a feedback. What is the open loop gain? Meaning that when there's no feedback for this circuit. A1. What is the feedback factor? Definition first. K equal to what? By definition. XF divided by Y. Definition, right? Because this is the output. I'm getting this much to do the feedback, right? So what is XF divided by Y? He say R2 over R1 plus R2. Do you agree? What are we using? Voltage divider, right? Cool. Then what is the closed loop gain? Maybe you forgot the equation. Let me write it again. This is the equation we just derived, which is equal to A1 divided by 1 plus R2 divided by R1 plus R2 times A1. Can you compare these two? They are the same, right? So this is another method. If we recognize that this is a feedback circuit, cool. We can use our feedback theory to do it also, instead of doing KCL, KVL. Okay? And of course, it's worth to note the comparison here. How does it do the comparison? Because we have y equals to A1 times x minus xf as an op-amp. X minus xf times A1 becomes y, right? This part is the comparison, is the built-in comparison already. Okay? And negative feedback because it's minus. So if you have a good feedback system, what will happen to the feedback signal? It will be interesting to see, right, how much I get punished by exceeding the speed limit, right? It turned out that X and XF trace very closely to each other if you have a good feedback system. Okay, let's take a look. This equals to X minus XF, and what is XF? And I define something called error, E. E equal to X minus XF. What is XF? Well, again, it is equal to Y times K. And then I continue. Y is just equals to A1 times K. Oh, you're doing E already. Actually, I got lost. A1 times K, and then times X minus, no, actually I should not do that, otherwise I will screw up. I won't do that. But what you're saying is good, actually. What you're saying is good, to put the E, right? But I will just use my method in my cheat sheet. So this equals to K. What is Y in terms of X? We already learned that. What is Y divided by X? What type of gain is that? How do we call it? It's called closed loop gain, right? So this is just ACL times X, because Y equals to ACL times X by definition, by closed loop gain. But I already know what is ACL, right? ACL is what? Do you remember? The closed loop gain was that? Yes, someone already memorized it. A1 over 1 plus KA1. A1 over something, 1 plus KA1. Cannot be wrong, right? Times X. So I'm going to take out the X, and this becomes 1KA divided by 1 plus KA1. I just take the X, factorize it. And of course, this becomes X divided by 1 plus KA1. Okay? Now, if KA1 is large, now this is something called loop gain we will study later. Then what will happen to E?
Will be
Very small. Okay, so if you design a feedback circuit, you should expect this one is very close to it. And you say, wow, if very close, then am I going to have gain? Yes, because you have a large gain in A1. Now this one is very useful to myself when I design a feedback circuit. It doesn't work. And to trace the error, sometimes I just probe this tool. And then if I don't see they trace each other, I know my feedback circuit is not working. If they trace each other, then maybe it is working, but I just have the wrong parameter. My original design has some problem. Just the gain is not good enough or whatever. Okay, so just want this, I want you to have this idea that when you have a good feedback, the input and the feedback trace each other well. Okay, this is the only thing I want you to have it in your database. So he asked if K is positive. That depends on your purpose. we are talking about negative feedback, right? So in order to have negative feedback, I want to have x subtract something proportional to y. Then if k is negative, then I'm going to add something proportional to y, right? So you are double negative, then you becomes positive feedback. So later we'll see that under some frequency, the k becomes positive, negative. Then you will go to oscillation because of positive feedback. So here we all assume positive. Okay?